Imagine someone tells you there is an entire planet hiding inside our own solar system. Not behind a cloud. Not on the far side of the sun. Somewhere beyond Neptune. Nobody has ever seen it. No telescope has photographed it. No spacecraft has flown anywhere near it. And yet, many astronomers think it may be there. That sounds impossible, because it almost is. Normally, a planet is discovered first. Only then do scientists begin asking questions about it. This story unfolded the other way around. Long before anyone talked about a hidden planet, a few frozen worlds at the edge of the solar system had already begun doing something strange. They were so distant that most people had never heard their names. Tiny worlds, barely visible even through powerful telescopes, drifting through regions where sunlight is little more than a faint glow. Individually, they weren't especially remarkable. The outer solar system is full of odd objects. Finding one with an unusual orbit isn't surprising. Finding two isn't impossible. Even three could simply be bad luck. But the list kept growing. Different telescopes found them. Different surveys recorded them. Years separated many of the discoveries. There was no obvious connection between the teams that found them. Only after their orbits were placed on the same map did something quietly begin to stand out. The long, stretched paths of these distant worlds didn't scatter in every direction as astronomers expected. Instead, many of them seemed to lean toward the same part of space. Not perfectly, but enough to make people look twice. At first, almost nobody treated it as anything more than an odd coincidence. After all, space is messy. Gravity has been throwing small worlds around for more than 4 billion years. Strange orbits are part of the landscape. One unusual pattern doesn't rewrite the solar system. The simplest explanation was also the most comforting. Perhaps astronomers were fooling themselves. Telescopes don't watch the entire sky. They observe certain regions during certain seasons. Some areas are easier to search than others. Some are almost impossible because dense fields of stars hide faint moving objects. If you spend years looking in the same kinds of places, perhaps you'll keep finding the same kinds of orbits. It was a perfectly reasonable idea. In fact, it became one of the strongest arguments against taking the alignment seriously. So instead of asking what might be pulling these distant worlds together, researchers first asked a much less exciting question. Could the pattern disappear if they accounted for where they had been looking? They reconstructed old surveys. They mapped the parts of the sky each telescope had covered. They estimated which distant objects would have been bright enough to detect, and which would have remained invisible no matter where they were hiding. If the alignment was nothing more than an observational illusion, this was where it should fall apart. It didn't. The statistics changed. The level of confidence changed. But the distant worlds still refused to spread themselves randomly around the sun. Something about their arrangement survived every attempt to explain it away. That didn't mean a hidden planet suddenly existed. It meant the easiest explanation had become much harder to believe. And once that happened, an uncomfortable possibility began to replace it. What if those frozen worlds weren't shaping the mystery? What if they were only tracing the outline of something much larger that no one had ever seen? Finding an answer turned out to be much harder than finding the pattern. Nothing in the known solar system was supposed to keep these distant worlds arranged this way. Neptune was the obvious suspect. It is the outermost giant planet. Its gravity has spent billions of years scattering icy bodies into the far reaches of the solar system. Many of the strange objects discovered beyond Neptune owe their existence to those ancient encounters. But these worlds lived too far away. Take Sedna, one of the first objects that drew serious attention. Its journey around the sun lasts roughly 11,000 years. Even at the closest point in its orbit, it remains far beyond Neptune's normal gravitational reach. It never swings close enough for repeated encounters. It never passes through the region where Neptune usually reshapes an orbit. If Neptune had thrown Sedna onto its present path, it somehow managed to do so without ever coming close enough to finish the job. The same problem began appearing elsewhere. Another distant object, then another. Again and again, astronomers found worlds whose closest approach to the sun remained detached from Neptune's influence. Each one could still have its own history. A passing star in the sun's crowded birth cluster might have disturbed one of them billions of years ago. Perhaps another had been nudged by a chain of unlikely encounters. There was no shortage of possibilities for explaining a single object. The difficulty was explaining all of them at once. Whatever had happened seemed to leave behind the same signature. Long, stretched orbits, detached from Neptune, leaning toward the same broad region of space. Nature rarely repeats itself so neatly without a reason. That realization changed the question. Instead of asking how each distant world reached its orbit, astronomers began asking whether all of them had been responding to the same influence. Not a violent collision. Not a brief encounter billions of years ago. Something that could still be there today. Something capable of quietly shaping these orbits over immense stretches of time. Gravity has one remarkable property. It doesn't need to be seen to leave a trace. Long before Neptune was photographed, its existence was inferred because Uranus refused to move exactly as predicted. The unseen planet revealed itself by disturbing another world's orbit. The outer solar system seemed to be offering a similar challenge. No unknown planet had appeared in the telescope. No new point of light had been announced. Only the motions of distant worlds. If something massive was hiding beyond Neptune, its gravity would not simply pull one object. Over millions and billions of years, it would slowly reshape entire families of orbits. For the first time, astronomers had enough observations to ask whether such a world could actually exist. Not where it was. Not what it looked like. Only whether a single unseen object could naturally produce everything the distant worlds were already doing on their own maps. The next step would not begin with another telescope. It would begin with mathematics. The idea sounded almost impossible. How do you describe a world that nobody has ever seen? At first glance, the question doesn't even seem scientific. Without a photograph, there is no size to measure, no atmosphere to study, no surface to examine. Nothing. Only empty space. But gravity has a habit of revealing things that light cannot. If an unseen object is massive enough, it doesn't need to announce itself. It only has to disturb everything around it. That was the approach a group of researchers decided to test. Instead of searching the sky for a missing planet, they started with the orbits that already existed. Imagine placing thousands of tiny steel balls onto a stretched sheet of rubber. Now hide a heavy weight underneath. You never see the weight itself, but the paths of the balls slowly begin to curve around it. Given enough time, those curved paths can tell you surprisingly much about whatever is hidden beneath the surface. Gravity works in much the same way. The frozen worlds beyond Neptune had been moving for billions of years. Every lap around the sun recorded another tiny gravitational nudge. One encounter would mean very little. Millions of years of motion could leave behind something far more difficult to erase. Researchers built computer models of the outer solar system and began adding an extra planet. Not just anywhere. If such a world existed, its gravity would have to keep those distant orbits clustered instead of allowing them to spread randomly over time. Most imaginary planets failed almost immediately. Some scattered the distant worlds too violently. Others destroyed the alignment altogether. Many simply produced a solar system that looked nothing like the one astronomers had observed. The possibilities narrowed surprisingly quickly. The simulations kept returning to roughly the same kind of world. Not another Jupiter. Not a small, rocky planet like Mars. Something in between. A planet several times more massive than Earth, traveling on an enormous, elongated orbit hundreds of astronomical units from the Sun. The exact numbers shifted from one model to another. The general picture did not. Even more surprising was what happened next. The same simulations began producing something nobody had used to build the models in the first place. A small population of distant objects with wildly tilted orbits. Some climbed far above the flat plane where most planets travel. Others swung through the solar system on paths that were almost perpendicular to everything else. The models hadn't been asked to create those objects. They simply appeared as a natural consequence of the hidden planet. That raised another question. If this picture was even close to reality. Did those strange, highly tilted worlds actually exist? Astronomers didn't need to wait for new observations. They searched through existing catalogs instead. And there they were. Objects that had already been discovered years earlier. Ignored at first because they seemed too unusual to fit anywhere. Now they fit somewhere. Not as proof, but as one more piece of a picture that was becoming increasingly difficult to dismiss. For the first time, the invisible world was doing more than explain old observations. It was correctly anticipating new ones. None of this proves Planet 9 exists. A successful simulation is not a discovery. It is only a test. The real question is whether anything simpler can explain the same observations. Some researchers believe there might be another answer. Instead of one unseen planet, perhaps countless smaller objects beyond Neptune collectively exert enough gravity to organize the distant orbits over billions of years. Others continue to argue that the pattern itself may still be influenced by where astronomers have searched and, just as importantly, where they haven't. Those possibilities haven't been dismissed. They're still being tested. That's exactly how this story has unfolded from the beginning. Every explanation has been challenged before being accepted. Every new result has had to survive someone trying to prove it wrong. And so far, the idea of a distant planet has survived remarkably well. Not because every alternative has failed completely, because no alternative has yet explained as much with so little. The same hidden world offers an explanation for the clustered orbits. The same world naturally produces the strange population of highly inclined objects. And the same calculations begin placing limits on where that world could actually be. Ironically, that's when the biggest question returns. If astronomers can estimate its orbit, why hasn't anyone found it? Part of the answer is simply distance. Neptune circles the Sun about 30 times farther away than Earth. The proposed orbit of Planet 9 begins far beyond even that. Depending on where it happens to be today, it could lie hundreds of astronomical units from the Sun, moving so slowly that years of observations might reveal almost no motion at all. brightness becomes another problem. A planet doesn't shine by itself. It reflects sunlight, and sunlight grows dramatically weaker with distance. By the time it reaches the outermost parts of the proposed orbit, the Sun is little more than an exceptionally bright star. The planet would receive only a tiny fraction of the light that reaches Earth. Then it has to reflect that faint light all the way back again. Even a world several times more massive than Earth could appear as nothing more than an extraordinarily dim point buried among millions of background stars. The sky itself doesn't make the search any easier. Some of the remaining search region overlaps dense star fields near the plane of the Milky Way, where countless faint stars crowd together in every image. Finding one extremely slow-moving object against that backdrop is less like spotting a lighthouse on an empty coast, and more like noticing that a single grain of sand has shifted on a beach. That is why the search has become less about luck and more about elimination. Wide-field surveys have already ruled out large portions of the sky. Every season removes another set of possibilities. Every image that fails to reveal the planet still narrows the places it can be hiding. The photograph everyone wants may never arrive by accident. It will almost certainly be the last step in a search that has already spent years shrinking the darkness around an object no one has ever seen. That search is still underway. On clear nights, some of the world's largest telescopes continue sweeping across carefully chosen regions of the sky. Not because astronomers know exactly where Planet 9 is, because they now have a much better idea of where it probably isn't. Every survey quietly removes another piece of the map. A bright object that should have been visible in one region and isn't can be crossed off the list. Then another. And another. The search area becomes smaller. Not dramatically. Patiently. One of the most important tools in that effort has been the Subaru telescope in Hawaii. Its wide-field camera can capture an enormous patch of sky in a single exposure, making it especially useful for looking for objects that move only a tiny distance over many months. That slow motion is exactly what astronomers expect. If Planet 9 exists near the farthest part of its orbit, it would spend centuries creeping across the sky almost unnoticed. A nearby asteroid races from one image to the next. Planet 9, if it is there, would barely seem to move at all. Ironically, that makes the search even harder. Modern telescopes are designed to notice change. A faint point of light that hardly changes from one season to the next is easy to mistake for one of the countless background stars scattered across the Milky Way. Finding it isn't simply a matter of seeing something faint. It's a matter of recognizing that one faint point doesn't quite belong. The coming years may change that. A new observatory, the Vera C. Rubin Observatory, has been built to survey the southern sky again and again with extraordinary depth. Its mission isn't to hunt Planet 9 specifically. It is designed to watch the changing sky itself, night after night, year after year. That repeated coverage could reveal objects moving so slowly that previous surveys struggled to separate them from the background. Just as importantly, it could eliminate large parts of the remaining search space if nothing appears. Either outcome matters, because this story has never depended on finding the answer everyone hoped for. It has depended on following the observations wherever they lead. If Planet 9 is eventually detected, the discovery will not begin on the night someone notices a faint, moving dot. It will have begun decades earlier, when a handful of frozen worlds refused to wander randomly through the darkness. If future surveys search every remaining corner of the predicted orbit and find nothing, that result will matter just as much. It would force astronomers back to the beginning. Back to the strange geometry of those distant orbits. Back to the question that started all of this. Because those worlds are still out there. Their paths have not changed. They still sweep around the sun in the same unexpected arrangement. They still describe a solar system that appears ever so slightly incomplete. Somewhere beyond Neptune, there may be another planet. Or there may be something even stranger that no one has imagined yet. For now, the only honest conclusion is also the most remarkable one. An entire world has not been discovered. Yet the motions of distant, frozen bodies have been enough to convince many astronomers that it is worth searching for one. The photograph is still missing. The reason for looking is not